All right. Well, here's what we're going to do. To start this lesson off, let me adjust my screen just a wee bit. There we go. We're going to see how you guys did on these factoring problems. This first one is the difference of cubes. So we got 2x and 3. Those are my a and b values. So I got 2x minus 3, and then I got 4x squared plus 6x plus 9. Does that shake out with what you guys got? Yeah. All right, that's the difference of cubes. Kenneth.
I was just going to ask.
Oh, you go on with your bad self. Let's see here. Number 2, we said was magic method. What'd you guys get on that one? Save me a little time. 3x what? No, that ain't good. 3x plus 1. Well, it ain't going to be 3x and 3x because it's supposed to be x minus 7. All right, now how could this sounds suspicious to me. No offense to you guys that were helping me. But this sounds suspicious. So how could I check to make sure I like this answer? Boil it out. Let's do that. So 3x times x, ding. Outer gives me negative 21. Inner gives me positive 1. So that looks like negative 20. Ding. And then negative 7. All right. Thumbs up. Well done. Let's go on to number 3. And this one we said was a magic method. Why don't we work this one out? I think a few of us had kind of asked. So I know right off the bat that I'm shooting for something that looks like this. 2 and 3 structurally are going to be similar. It's just that I know this is going to be something x squared, right? Okay. Now, along those same lines, I look at 7 and I think, oh, well, 7 is prime, so it's only going to be able to be a 1 and a 7. And then I could sort of, like with regards to 6, I'm just doing guess and check at this point. I'll show you magic in just a moment. But like with regards to 6, it's either going to be 1 and 6, 2 and 3, 3 and 2, or 6 and 1. All right. You know what I'm saying? So like, for example, if I did 6 and 1, that's stupid because the outer is going to make 42, the inner is going to make 1, and that ain't 43. So like, I know that wouldn't work. What if I did 1 and 6? Well, then the outer gives me 7, the inner gives me 6, and that would make 13. So that ain't going to work. Right? So this one's not bad because 7 is prime. Let's try 2 and 3. Okay, so the outer would be 14, the inner would be 3, 14 and 3. There's my answer. So that's sort of a guess and check approach. I don't like that approach because it's time intensive. It takes a long time. Here's how the magic method would work. Okay, we would say x to the 4th plus 17x squared plus 42. That's taking 7 and 6 and multiplying the two of them together. And then that's going to be x squared plus 14. X squared plus 3. And then that leading coefficient is going to come back, and we're going to kill off any common factors. Now, what's the common factor from the first pair? Fredo, pay attention. 2. So we got 3x squared plus 7. And what's the common factor on the second pair? 3. Good. So we got 2x squared plus 1. And there you go. That's that answer. Nash, that would be kind of how I would recommend working through this problem. And Blake and Zach, y'all don't be distracting folks. I think I might call you Zach again. Blake and Mitch, y'all don't be distracting folks either. I'm sorry, what'd you say? Okay. Accuse you of trying to distract. I accuse you of distracted. And you were distracting me at least. Now, Blake, we're not stabbing anybody in the butt, especially not sweet little Fredo, okay? So dadgum. Hey, who voted? Yeah, Fredo. I like him. Fredo's a sweet guy. You don't poke somebody in the butt. Dadgum.
Fredo, man. Fredo, do you want to
What?
Who volunteered to do number 4?
Kenneth.
Kenneth Mulatto. All right, baby. What we got? You should do grouping. Did you group the first 2 and the last 2? Okay. So what's in common with the first 2? And what's left over? What's in common on the second two? And what's left over? Beautiful. All right, so you got x squared minus 4. Break that down. All right, and then you had x minus 9 as well. X minus, no, don't daggum square it. Because what did we start with? What kind of, Franklin, what kind of polynomial is this? Classify it qualitatively. It's a quadrinomial. That's quantitatively. I want qualitatively. In other words, what type of term is this?
A third degree.
This is Franklin's question. And what do we call a third degree term?
No, not trinomial.
I'll give you a hint. That good. Cubic. Okay, so it's a cubic, and therefore it should have how many linear factors? It should have 3. Why does this keep moving, doing stuff? Distracting right here.
Yeah, right in.
Why are you talking across the room, Ken? You think just because you do a grouping question, you can distract me and Fredo again?
Well, actually, Fredo was distracted.
He's distracting you.
That's cap, coach.
I'd be all money on that.
Yeah, Blake got my install for the products.
That's cap.
Kenneth,
K-cap.
See, dirty old Kenneth back there
K-cap.
is trying to throw sweet Fredo under the bus,
Again.
and I ain't having none of it. What do you mean again? Again. Fredo don't belong under the bus. All right. How about number 4? Number 4, grouping again? What do you think, Stephen? You got me? Oh, that's interessante. So he's going to group these two together and these two together. All right, what's in common between the two I circled? And what's left over? And a 1. All right, what's in common between the two I underlined? A 2, and what's left over? All right, and so you're going to get an x plus 2, and then hold your horses, fellas. You're going to get an x plus 1 and an x squared minus x plus 1. Where did that come from? The sum of cubes. How now, brown cow? What was, I asked Franklin this a second ago. I'll throw this back to Mario. Mario, what was the degree of this polynomial in number 5? It is degree 4. It's a quartic polynomial. And therefore, how many linear factors could I break it down to? 4 linear factors. Except I've got 1, 2 linear factors and then a quadratic factor. If you were going to, this one don't factor anymore, but if you were going to break it down, you would have to break it down using the quadratic formula, which we won't take it any further because that would be ludicrous. Blake.
How do you go from x to x cubed?
Here to here. All right, there's an intermediate step that I skipped over, which would be x plus 2. What we factored out from each group gets its own parentheses, and x cubed plus 1, the remainder, if you will, or the leftover, gets its own group. So we wrote this as a product, and to factor something needs to write it as a product, but x cubed plus 1 could be broken down further as the sum of cubes. So in other words, we needed to take this and write it as a product there. Okay, and that's the sum of cubes. What about number 6? Moving on here with this last one. And this factoring review is, I know we're taking our time on it, but it is very vital. It's super important. Now, I've heard from Stephen, I've heard from Mario. Give me some fresh blood, Finley. I've heard from you yet?
No.
Wake up and welcome to the party, baby. What we got on number 6?
I multiplied 2
2 what?
x.
2x. Good. So we take out a 2x, and we're left with 81x to the 4th. That smells like a perfect 4th to me. Okay, and then we take out a 2x from the second one. Freddie, help me out. What's 512 divided by 2? It is 256. Now, Phil, that's a what? That binomial is a what? It sure is. Different squares. Mitch factors as a binomial times its conjugate. Very nice. So we got 2x And then what do y'all think? 9x squared plus, I always do the plus one first. That's because I'm, all right, good. And then 9x squared minus 16. But 9x squared minus 16 would be another different square. So can we go ahead and say 3x plus 4? Oh, slow your roll. And 3x minus 4. All right. And then at this point, Mitchell is absolutely correct that this, this is the sum of squares. So we're going to be sending out an SOS. And therefore, it's going to be a complex number times its conjugate. Y'all like the police, don't you? Plus 4, 3x minus 4. Oh, good golly, Miss Molly. So what's in green, Eli? No, baby. We said complex number times its conjugate. Tell me what to fill in. Three x.
I got it.
He was trying to answer for you. I was distracted. I thought I heard you say something that besides just plain old 4. Ah, good. 4i and negative 4i. All right. Brush off them haters, Mitch. Brush off them haters. So here we go. This was, Christian, this was degree what? Degree 5. And we wrote it as a product of 1, 2, 3, 4, 5 linear factors. So if this had been set equal to 0, if it had been 162x to the 5th minus 512x equals 0, we would have how many answers?
5.
What would those answers be, Henry Heil? Run through the list. Get me this answer.
Oh, 3x 4i.
Yes, I was in.
Set 2x equal to 0 and solve. Michael, help him out.
0.
Okay. That's okay. I phrased it poorly. Henry, if this had been an equation right here, I'm looking for 5 answers. And you better give me an answer for each individual factor per the ZPP. All right, so what would that first answer be? That boy. Okay, good. 0. Now, continue running through the list, Mr. Howell. What's the next answer going to be? No, you didn't have to. This is icing on the cake. Negative 4i over 3. And then the next one will be positive 4i over 3. So we'll say plus or minus 4i, or 4/3 i. Let's say it that way. I like that better. Plus or minus 4/3 i. And then what would our, let's share the fun here. Fredo, finish it up. What would our last 2 answers be? Fredo, if you had, go ahead. Good. Plus or minus plain old 4/3. Finley, nobody asked you to talk. I love being so mean to Finley. It is so fun. What you got?
So, in like just in a test, are you gonna specify if you want us to keep going with complex numbers?
All right. So if you didn't hear Mitchell's question there, the word completely at this point means take it as far as you can take it. And therefore, if I've taught you how to factor the sum of 2 squares, you're expected to take it down. But if I've got, like, look over here at this trinomial, I can't break this down any further as far as factoring goes, Aiden. I can't break it down any further. And so, like, I wouldn't be expected to take this yellow trinomial and to break it down. It would just be, we've gone as far as we can go. But if I left this as 9x squared plus 16, then I'm saying, ooh, I forgot. He told us go from green to green. He's taught us that, so we should know. All right. Now that we've gotten this review out of the way, and we spent a good amount of time on that review, okay, we're going to get into now what is called the rational root theorem. The rational root theorem. It looks crazy. But here's the rational root theorem, Freddie, in a nutshell for us. Okay? I will give you a polynomial function, much like this one, right? So we had said, I think Mario answered a minute ago, he said this is an example of a quartic, degree 4. So how many roots will this polynomial have? It's going to have 4 roots. Aiden, you with us? You good? You look like you're struggling. Okay, it's going to have 4 roots. And what we're going to do is we're going to, Finley, turn around. We're going to cook up a list of possible rational roots. Now, Michael, remind me what the word rational means. What's the base of the word rational? Ratio now. Good. So a rational root is a root that can be expressed as a ratio of integers. In other words, it's a terminating or repeating decimal. It's a nice fraction or integer. So in other words, it's not complex and it's not irrational. Okay, so no like square root of 2s, no i's, no nothing like that. We're going to use the rational root theorem says that we can focus in on 2 things. We can focus in on the constant and we can focus in on the leading coefficient. There's the leading coefficient right there. There's the constant right there. And the leading coefficient we'll call we're going to set up a list of factors. We're going to call that letter P. P is a possible factor of the leading coefficient. Freddie, I want to see eyes open, bub. All right, eyes open. So if P is going to be a factor, Freddie, give me some factors of 6. What are all the possible factors of 6? All right, you left out half of them. I'm asking dadgum Freddie. Batman back there answering for you. Good, good. So we can slap a plus or minus in front of each of these. All right, Kenneth, how about you take care of the constant? What are the all the possible factors of -10? Pause just for a sec, Kenneth. Mitch brings up a great point. This is too much to write down. Do not try to write down. This is a good like teachable moment for you guys, like in all of your classes. Do not try to write down everything that you see on the screen today. That sounds like a you problem. Figure it out. Okay, so I had a class one time with Brother Walter at CBU. Brother Walter was awesome, and he was teaching a class that's called Real Analysis. This is a senior level, 400 level class, and there was 4 kids in the class, me and 3 other folks, and it was super challenging because he had a buttload of stuff. Like for an hour and a half, he would hit us up with all of this stuff. And early on in that semester, I was trying to write down everything, And Brother Walter would just like go through it so fast. You remember Bro Wally? And so like finally I was like, Brother Walter, you got to slow down. He was like, no, you got to quit trying to write everything down. Right? And so like with stuff like this, do not try to write all these words down. Just read them, pay attention to what they say, and then get the gist of them by looking at the example. Do you concur with this, Mr. Pete?
He also, Brother Walter had this, he had all his notes and then they're written out, he had a sheet of paper on top of them. And he pulled it down line instead of writing. Line at a time.
So he wasn't even taking the time, like you wouldn't see his pencil moving, his pen moving. He was just like slowly.
He was moving faster than he could write.
Yeah.
So, yeah.
But anyway, the point I'm making, and Mitch brings up a great concern here, like you will not be able to write down everything that you think you need to. Get the meat and potatoes, and then
you can always Google the rational root theorem later if you wanted to write it down.
Yeah. And they should know this also. This snip came from our what?
Textbook.
Came from our textbook.
Yeah.
Yeah. Kenneth, question.
So which should be rational?
Oh, okay. So it was the phrase that I'd used, like the Coach Morgan summary, if you will, was saying that the rational root theorem is going to allow us to come up with a list of possible rational roots for any given polynomial function. A list of possible rational roots for any given polynomial function. And then we discussed, like Michael helped me talk about like what rational means. And so therefore, all right, so back to Kenneth. Kenneth, you've had a little bit of time to consider your answer in relation to Freddie's answer. What did you leave out? Louder? Good, good, good. So we got positive and negative, positive and negative. All right. Where did the list of P come from?
Leading coefficient.
Leading coefficient. Where did the list of Q come from?
No constant.
The constant. Now, here's where we get to have a little fun. We're going to mix and match. We're going to mix and match. We're going to do P over Q.
I'm confused.
All right. I'm listening. Go for it.
So how did we get those numbers from?
All right. So the number 6, this is important. The number 6, when you think of its factor pairs, 1 times 6, 2 times 3, -1 times -6, and -2 times -3, that's our list of 8 factors that's right there. And 10, or -10, even if you wanted to play it that way, 1 times -10, 2 times -5, 5 times -2, and 10 times -1, that's our list of Q's. They pay me to answer questions. So you guys have to ask questions like this. Good question. Anybody else?
Why do we put it?
Yes. Okay. So here's what we're going to do. Now we're going to, well, I told you we're going to have a little fun. We're going to mix and match. Okay. So in other words, we're going to take a number from our first list and divide it by a number from our second list and see what shakes out. Okay. Now I recommend that you do this in an orderly method. Take note that I'm speaking slowly, and you should probably hear and heed what I'm saying. Do it in an orderly fashion. Here's the orderly fashion I recommend. I think start with +1 and divide it by each and every Q value. And then go with -1 divided by each and every Q value. And then do 2 and -2 and then 3 and then -3 and then 6 and -6. And you'll find that some of them repeat. For example, right? For example, when we get to 3/1, what's 3/1? 3. And when we get to 6/2, what's 6/2?
3.
So that some of them will repeat. And we don't want to waste time by writing up all the repeats. We have to be clever about this. All right, so here we go. Mitch, I'm going to get rid of these 2 lists so I'll have plenty of room. You want to help? Oh, man, I was hoping somebody would volunteer. Thank you. All right, so Mitch, let's start out. What do we got? 1/1 is 1. What's 1/-1? So really, we'll get in the habit of just slapping a what in front of everything. Plus minus. Freddie, eyes. Thank you. I'm sorry, do you have something to say? Oh, you just might be sleepy, that's all. But if I see those eyes closed, I'm well within my rights to help you by calling your name. Just keep them open, baby. He's like, I was blinking, Coach Morgan. No blinking allowed. All right, Mitch, continue. Good, so we'll do ±1/2. Excellent, keep on rolling.
Plus or minus 1/5.
All right. Eli?
Anyway, we can just plus or minus.
No,
You have to keep writing plus or minus.
each individual one. Steven, what's that?
There's like a faster.
You?
Use a calculator, maybe.
Well, that's cheating.
Hey, use this one.
So Mitch helped me with my first one. Now, how about we move on to 2 over all 4 of those, and we'll kind of speed up the process. 2/1, 2/2, already on the list. 2/5, is that on the list? 2/10, is that on the list? Yes, because 1/5. So what we're doing is we're going to start saving a little. So 3/1, that's not on my list. So ±3. ±3/2. ±3/5. ±3/10. All right, Finley. Grab it. Already got that. Six over 10 is 3/5, which we've already got. So I think our list is complete now. Now, how many possible rational roots? How many possible rational roots are on that list? Let's go. Let's see here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 4, 24. Woo! Okay. So can you guess where we're going next?
Finding like terms. Graphing.
Yes and yes. Guess and check, graphing. All right. So in other words, how many was it? 24? Does this polynomial have 24 roots? Okay. How many roots does this polynomial have?
4.
It's got 4. Are they guaranteed to be rational? No. So it might have 4 irrational or complex or imaginary roots or whatever. Who knows? But listen carefully. If it has any rational roots, they are going to be on this list. If it has, listen to that again. If it has any rational roots, they will only come from this list. Now, what we will do is we will take this list and we will start trimming it down. And one of the best ways to trim it down in my mind is to look at the graph. Okay, so I'm going to look at the graph now. You guys on your graphing calculators, why don't you practice with me? Okay, since I'm always trying to teach you a little bit more about your calculators, why don't you practice with me? This is a skill that we've done before. Okay. This is a skill that we've done before. We're going to take, now let me get this out of the way. We're going to take our y equals screen, and we're just going to type in that function that's at the top. Now, that's a lot to type in, so just bear with me. 6 x to the 4th minus 43 x to the 3rd plus 66 x squared minus 3x minus 10. All right, and I want to double check to make sure I've typed everything in correctly. 6x to the 4th, 43x to the 3rd, 66x squared, minus 3x minus 10. All right, and so if I hit zoom 6 to make sure I got a standardized window, not a very helpful window. That kind of looks like this first window, but I can adjust the window a wee bit. Okay, I can adjust the window a wee bit by hitting the window button and saying, man, I don't really need all of that stuff to the left. Maybe we could just go like -3 to the left. And then I need to go down pretty far. So I don't know, like -100. I'll just make something up. Maybe I need to go up a little bit more. So I'll just do 35. And I don't want 135 tick marks. So I'll make a tick mark happen every 5 units. Then I can hit graph. Did I go down far enough? No. So I go back to window. And instead of -100, maybe I could do like, I don't know, -160. And then we'll go up to 40, and we'll make a tick mark every 2 units or every 20 units on the y-axis. I really didn't need all the space to the right either, so we'll make our x max 8. We'll hit graph. Still hadn't gone down far enough, but we're getting better. -200, do you like that? 200. And then let's go up. Let's go up a little bit more. Let's go up to 80. Oh, baby, that's a good looking graph right there. I can see all the curves. I can see all the mins and maxes. I can tell where it crosses the x-axis pretty easily. Now, you might take a minute or so to get that locked in on your graph. So practice. Very nice. Practice. Make your graph kind of try to look like my graph. And then as soon as you want to go back to your standard window, hit zoom 6. I wouldn't do that yet, but like when you leave this example, leave this class today, zoom 6 takes you back to your standard window. Blink. Zoom 6. Zoom 6 was standard window. And then the button next to zoom is window right up there, and you can make your window look like this. Mario, are you and Kenneth helping each other? You good?
Yeah, mine's not doing stuff on my calculator.
Do you have a plot highlighted on your y equals screen? Hit y equals. If one of these plots is highlighted, scroll up, hit enter, and unhighlight them. And then you'll be freed up.
Okay.
Now, oh, go ahead, Christian. Sir?
Like,
On the window button, I just made a Y scale 20. What that means is every 20 units on the Y axis, we have a tick mark, just so I didn't have 280 daggone tick marks clogging up my Y axis. You know what I'm saying? Makes it look nicer, just like that. There we go. So of these roots, now let's see, how many times does this, Franklin, how many times does this cross the X axis? Bingo. So all four roots are what? They're not rational necessarily. Real. Who said that? Very good. They're real roots. All four of them are real because we see them passing through the x-axis. They might pass through at irrational numbers, though. But do you remember how to find them? Remember how to find them? Here we go. I'm going to guess this looks like -1/3. That first root looks like -1/3. So I hit trace -1/3. And oh, yeah, look at that. I picked a number from my list and it worked out. That was great. Where does this other one look like? 1/2 maybe? So 1/2. I hit enter and oh, that was a good guess. There we go. Now let's see here. What if I put in 3/10? 3/10. It is right. -1/3.
Third is my.
Oh, 3/10, is it?
That's not a-
Close.
Holy moly. Let's see where I messed that up. Mitchell, good for you being observant. I was going to type in 3/10 and be like, see, that's not a root. What did I do? -1/3. No, -1/3. Franklin, what's up?
Here's the next one.
Well, hold on though. I'm having an issue here because this is a rational root. -1/3 is a rational number, and yet it wasn't on my list. Just because I'm recording this and we're going to run out of class time, let me make a note to do some investigating on what's going on. I've made a mistake somewhere, and I want to find it so that y'all don't lose faith in the rational root theorem.
I lost what he said.
Oh, stop it.
Well, close to mine. I don't think I have.
All right. So anyway, what I'm saying is that using this graph, it looks like we've got 1, 2, 3, 4 roots, and I think that 2 looks like a good possibility. So what am I prepping for here in Brown?
Synthetic division.
Synthetic division. And watch what we're going to do. Aiden, you with me? Watch what we're going to do. We're going to take one of our roots. I just picked 2. We're going to take 2 and we're going to cull it out. Now, if it is a root, Andrew, what type of remainder will I get? I'll get a remainder of 0 if it is a root. Okay. So let's run those numbers. I'll pull up a brown pen here. Do I even have a brown pen? You like that? All right. So we bring down 6. 6 times 2 is 12. -31. -62.
Yeah.
4, 8, 5, 10, 0. Oh, mama. Now, what's nice, and then Mitch, I'll get you. What's nice is,
Question. Thumbs up.
oh, sweet. What's nice is we will, now that we've pulled 2 out and we've got a remainder of 0, we can continue with the quotient and pull out our next one. All right, why is that? Because what we're doing is we're writing f as a product. So x minus 2, now we know is one of the factors. And guess what the other one is? 6x cubed minus 31x squared plus 4x plus 5. We just factored a big fat degree 4 polynomial. We wrote it as a product. Right.
So how do we know we're going to do synthetic division with 5 next?
Oh, it says in purple right there where I wrote up, it looks like 2 and 5 are good possibilities. Look like 2 and look like 5. And so now I'm like, I wonder if 5 is a root.
Isn't 3/10 the same as 4?
4x or 9.
Really close.
Hold up, I had like 6 questions all at once. So Mario, I don't see 5 on the list.
Coach Morgan, couldn't that have been -3/10 instead of -1?
Yeah, that's what it is. And do you think maybe the calculator was rounding? So -3/10. No, but it's not a root. See, because look at that, -1.95. I've got it written up to check. And I swear I don't. All right, well, let's see here. P is a factor of A naught. Oh, crap on a stick. Well, there you go, Mitch. Mitch. This is all Mitch's fault. You know why? Because Mitch is awesome and wrote all this down. And do you know what I did, fellas? Shame on me. You caught it on film today, too. If you've read, like Mitch wrote down what was up here, and I did not read through it. P and Q, I switched my list up. Crap on a stick. P is a factor of the constant, and Q is a factor of what? That leading coefficient. So I switched up my P and my Q. So this big old fat list of 24, that fixes the issue though, right there. This big old fat list that you and I comprised. Well, slow your roll. Instead of looking at the top list and dividing it by the bottom, just look at the bottom list and divide it by the top. All right, so I screwed up. I'm sorry. Lo siento. This is P. This is Q. Y'all make the adjustment. And I'm human and I make these kinds of mistakes more than I should. 1/1. We're going from the bottom to the top now. Yeah, I think that's bonus point worthy. 1/1, 1/2, 1/3, and 1/6. This reconciles the issue that we were having, though. 2/2 is 1, 2/3, and 2/6 is 1/3. That's already on my list. 5, 5/2, 5/3, and 5/6. Let's just carry on up here. And then we got 10/1. 10/2 is 5, 10/3. And then 10/6 would be 5/3, which is already on our list. There we go. So there's our full list. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Still 24 options. Well, I was going to give it to the person that brought it up, that pointed out the issue. All right, Michael.
So I, isn't it?
It is P over Q. I just called P the wrong thing. My P was Q and my Q was P. I messed that up. So make sure I go back and correct this. Make sure everybody understands. P is your list of factors of the constant. Q is your list of factors from the leading coefficient. And so here's how we'll fix it right here. It's going to be constant over leading coefficient. All right, A naught over A1. That's going to be how we comprise our list. And that makes me feel much better about Mitchell's comment with like that. Well, wait a minute, coach, -1/3 wasn't one of our roots on our list. Now it is. 2 is, and 5 is. So I feel much better. Honest mistake, but frustrating nonetheless. Hey, and you know what? When we go through and we start calling out these roots, are y'all comfy with how we called out 2 as a root? And we said we got remainder of 0, so it worked. What this other root, I suppose, is 5. That's on my list. When I test it out, let's see if it produces a remainder of 0 as well. What do you mean switch our numbers? No, 2 and 5 are legit. Good. Good. That's right. So like earlier, that crappy list that had come up where I did, like I called the wrong thing Q and the wrong thing P, it was the reciprocal. And so the true P over Q, in other words, constant over the coefficient, this is our legit good list. And we pulled out a few possibilities. We're like, ooh, 2 would be easy to synthetically divide, and 5 would be easy to synthetically divide. And what picture helped me determine what would be easy to test?
The graph.
The graph. And we said, well, hey, look, there's 2 and there's 5. So let's call that out. Taking it from degree 4 down to degree 3.
So the 5 is actually over the farthest over.
Well, watch this. So we took it from degree 4 down to degree 3, and then we took it from degree 3 down to degree 2, because we got x minus 5. And look at the resulting quadratic, 6x squared minus x minus 1. And I don't know about you, but I noticed that this one is factorable. And you know what one of the factors is? Just so happens to have negative 1/3 as a root. Could you tell me what that factor would be then? How about 3x? Aiden, you up? You with me? Roberts? 3x plus 1 would be that third factor. We just happen to stumble upon negative 1/3 as a root. And then whatever that next one would be, looks like that would be 2x minus 1. And so those would be our roots for this. So what would we do? We would solve it out. And we'd say, and I guess I got to end with this. What would this root be? 2, this root. 5, this root.
1/3.
Negative 1/3 in this root. 1/2. And that fleshes out with the picture that we've got right there. There were our 4 roots. 1/2 was one of the roots. 2 was one of the roots. 5 was one of the roots. And negative 1/3 was one of the roots. Mario. So the rational root theorem is what people used before calculators were created. Like how they would come up with a list of possibilities, and then they would call that list down. And they would, congratulations, by the way, you just solved your first degree 4 polynomial equation.
What?
You just solved your first degree 4 polynomial equation. You figured out all 4 of the roots. Now we're out of time. There is a delta math on this that we will look at when you come back on Monday after the break. Live Jesus in our hearts. If in the meantime you're curious about it, you can feel free to look ahead, but I certainly don't want to make that due on Monday. We'll talk about it Monday. Happy about what? You know what? Math is so nice because if you think